Okay, hello guys. So we continue with our study of sequences. So we're gonna do some more statements, sequences, but probably, so the topic's long. I think at some point I'm just gonna tell you the statements, and then we are gonna meet some proofs just to move forward to other topics. Okay. So last time we said we will prove this theorem. If A suited converges to A, then the sequence is convergent. See, this, if the sequence converges to a point, then the sequence is bounded. Okay. So last time we said, like, so if the sequence is convergent, so most of the sequence is around a point, right? Because you can put a neighborhood around the point A, and most of the sequence must be here. So some finite points must be outside, right? So the sequence is bounded. Okay, so it makes sense, right? So, and that's what we're gonna prove. We have a lemma saying that a sequence A should then converge to A if and only if neighborhood A contains all but the finite number of terms of the sequence. So that lemma, we didn't prove. We could use it, right? But since I didn't prove it, I think we're gonna try to do it directly. So let's try to prove this directly. So as I said, so if you have a sequence that is converging to A, right? Oh, but no, we're gonna use the lemma. We're gonna use the lemma. So let's say the proof goes like this. So we're gonna try to fix it on the way, right? So, but it's pretty much what I said. Like, if A is the limit of the sequence, most of the sequence must be around a neighborhood. So there is only a finite number outside of that neighborhood, right? So maybe we can say, let A be the point for which the sequence A to N, A equals 1 to infinity, is converging. Okay? It means, what does it mean? So as always, we start with the definition. What does it mean that the sequence is convergent? It means that, so ask yourself, what does it mean the sequence is convergent to the point A? So in particular, it means that if we choose epsilon positive, then by lemma 1, no, maybe not even by lemma 1, by the definition, by the definition of convergence. By the definition of convergence, for each epsilon, there is a positive integer n such that for all n bigger or equal than n, we have that there is an epsilon. Yeah, let's say it right. Not by lemma. We choose epsilon. Then by definition of convergence of A convergence to A, right? There is a positive integer capital N, such that for all n bigger or equal than n, we have absolute value of a n minus a is less than epsilon. Okay, right? There's a positive integer n. So that means, so what does it mean? So it's pretty much what we draw, like this is a minus epsilon, this is a plus epsilon, right? Because this is what it means, being the absolute value of a to the n minus a less than epsilon means this, right? We learned that, remember? We said this is a n minus a less than epsilon minus epsilon. And when you add a on both sides, this can cancel. So if I add a, add a, and add a, I obtain that that the sequence is, oh, sorry, me here. We obtain, oh no need to do that. This is means that the distance, yeah, maybe this is not that helpful. What it means is that the distance of an, right, minus a, this distance, right, that means the absolute value is less than epsilon, right? So that's what we get. Okay, so so what we're gonna do, what we need to do. So we need to find an n. So we need to find that the sequence is bounded. So what that means, we need to find, so what do you want? We need to find m such that the absolute value of n is less or equal than m. Okay, that means that the sequence is all over here, right, on the line, but there is an m, there is an n over here that is bigger than at any point of the sequence. Okay, so what we know, that an minus a less than epsilon implies an minus epsilon, sorry, an minus a is less than epsilon and bigger than minus epsilon, right? And adding a on both sides, we get adding a on both sides, we get a minus epsilon less than a plus epsilon. Okay, for all n bigger or equal than n. So what we are saying here, in other words, n is less than epsilon plus a. Okay. And but actually there is one that is just easier than that. And because I need the absolute value, right? So I need the absolute value. So there is probably, when you are doing a proof, there are many ways to choose your boundary, right? So this might be okay, but I'm thinking the sequence is not necessarily positive, right? So this to be bounded, probably it's better to it's probably okay to take it like that, but probably it's better to take the absolute value, right? So let me pause here for a second. Okay, so now my camera is activated. Okay, I want to make sure you guys can see me. So it's probably easier for you to see somebody, right? Okay, so yeah, so we wanna find some boundary. We wanna show that the sequence is bounded, right? I don't know. Let me change my. Actually, do it here. Okay, hello. Okay, let me do it this way because I know it works. Okay, hello. Okay, yeah. So that's one possibility. Okay. The thing that I don't like, and I check with the book, because the way that I wanted to do it was this. I think we did this for the homework, or it was a statement that we state as a proposition, and it says that this guy is bigger or equal the actual value of a n minus actual value of a. So I love that inequality, and I use it a lot. So I wanted to use that one, but I was thinking maybe this is enough. I don't need to do this one. But turns out that if I don't use this one, I have to establish a maximum boundary and a minimum boundary. That's how the book does it. Okay. So I'm gonna use this inequality because I think that's my style. So that's what I like. So you'll have this one. You can say an is less than epsilon plus a, but you will have to find a minimum too. Okay. So what I'm gonna do instead, to do it a little bit different than the book, is I'm gonna take the absolute value of the sequence. Okay. And that's a proposition we saw. So as I told you, you should stay to your own proof as long is correct, right? So something I'm gonna do is correct this part. So this is true, right? but I want to use the inequality. This is another way to do it. I mean, you start doing it like that, you can keep going, and then, but you have to have also a minimum. So this is true, right? We know that this is true. In particular, absolute value of n minus absolute value of a is less or equal than an minus a, right? But then if yeah, that's good. So, and this is less than epsilon, right? So that means that absolute value of an is less than epsilon plus absolute value of a. Okay, you see? So it has this advantage. I doing the absolute value for the I'm finding a boundary for the whole absolute value of a sub n, because a sub n could be negative, right? So when I take the absolute value, this will be absolute value of a plus 1. So I need the absolute value to make sure it's bounded. Okay. So that's what I choose this one better. It don't cause me doubts. Because I was doubting, do I need the minimum too? I need the sub and the if kind of. Okay. So now this is true. Remember, this all three is true is for all n bigger or equal than capital N. And so this is for all n bigger or equal than capital N. For n bigger or equal to capital N. So what we have is that for most of the sequence, let's say this is A, most of the sequence is less than epsilon plus A, absolute value of A. So most of the sequence is going to be below this in absolute value. Okay. But maybe A1 is here, or A2, A3, maybe A2 is here. Maybe A4 is here, but there are some finite that are bigger than epsilon plus the absolute value of A. Okay, maybe around here. This is epsilon plus absolute value of A. Okay. So what I can choose, if I choose M equals al maximum between epsilon plus A and all the others that are less than n. So A1, A2, A3, until an minus 1. Okay. It does my m, so I can count, let's say these are total, and the last one is an minus 1, let's say. Not necessarily, n minus 1 could be the highest, but you see. So most of the sequence is less than epsilon plus A, but A1, A2, A3, an minus 1 could be bigger, but n is going to be the maximum between all of them. These are finite. This is This is 1, 2, 3, n minus 1, n. So you can find the maximum of n numbers. Okay, and that's what we're doing. So we need to find m such that n less or equal than m. So for all n bigger or equal than 1. So let's check. This m works. So if an, so we have two cases. So let's say case 1. Case 1, n is bigger or equal than n. In that case, actual value of an is less than epsilon plus a, and in particular is less or equal than m, because m is the maximum of epsilon plus actual value of a plus other numbers. Okay, and case 2, n is less or equal than n minus 1. In that case, an, actual value of an, is less or equal to m, because m is the maximum of a1, a2, a3, an minus 1. So if n is any number less than n minus 1, is also less or equal than n. Therefore, an is less or equal than n, as we want. Okay? Okay, so that's the proof of that statement. So that's a very useful statement. So let's write the definition. What is divergent means? Definition: a sequence a sub n equals 1 to infinity is said to be convergent okay, if and only if there is a real number a such that a n equals 1 to infinity converges to a if actual value of n equals 1 to infinity is not convergent, it is said to be divergent. Okay? Okay. So if a sequence is convergent, the unique number to which it converges is called the limit of the sequence. So as I was saying, we're making the connection to limits. So A is the limit, okay? And that's the notation we're gonna use later. The book still doesn't want to introduce it. It just said in words that that unique number A is the limit. So keep in mind, limit of A sub n goes to infinity equals A. That's what we're defining here, okay? But the book it still doesn't want to say like that, so, okay. So we move next to what is called Cauchy sequences. So again, this is, this is another concept it's going to be useful later for your real analysis classes or your functional analysis classes. And so we need to talk about it. And then I'm gonna try to move, I'm gonna make a jump to make it a little bit more interesting. So more, and we're gonna talk about series. And all these concepts apply again. So, but not yet. So let's do Cauchy sequences. Cauchy sequences. I don't remember the right way to pronounce it. So, a Cauchy sequence. Well, let's write the definition, and then try to make the exercise to explain to yourself what it doesn't mean, to see if the concept agree with what I'm gonna say. So a sequence a to the n equals 1 to infinity. It's Cauchy, if only if for each epsilon bigger than 0, there is a positive integer n such that if m and n are bigger or equal than n, then absolute value of an minus an is less than epsilon. Okay? That's the concept of Cauchy sequence. And what it's saying is like, you can have A1 here, A2 here, A3 here, A4, but after certain n, let's say this is an, then the points cannot be separated. Okay? After some n, that sequence just, it is convergent. Well, we're gonna see that every in the real numbers, every Cauchy sequence is convergent. And we will need our main theorem of this class. The first main theorem of this class is called the Bolzano Weierstrass Theorem. Okay, so I'm not going to put that one because that's part of your real analysis class. I will let your advisor, your professor from real analysis to teach that, but we will use it. Okay, so that's first thing, important thing. We're not going to do Bolzano Weierstrass Theorem. That will be your real analysis class, and sometimes what they do is they evaluate the proof. Sometimes they will make you to prove that theorem because it has a lot of tricks, but really important tricks that it might be useful for later. Okay, so this is my Cauchy sequence. So what we're gonna do, we should prove this. Every convergent sequence is a Cauchy sequence. So the opposite, oh no, the opposite no. In the other direction is when we're going to need the Bolzano Weierstrass Theorem. The other direction is the arrow. Okay, so theorem, every convergent sequence is a Cauchy sequence. I'm really curious to see how you pronounce Cauchy. Cauchy or Cauchy? Okay. So let me give you a few minutes. So So I'm gonna give you a few minutes to try to prove this. Okay? So I'm gonna try to prove it too. So I'm gonna so I don't want you to see my screen, so I'm gonna stop sharing screen. So please let's spend 3-4 minutes to try to prove this by ourselves. Yeah, it's recording. So every convergence sequence is a Cauchy sequence. Hmm. So let me show you so far what I had done. So we compare and then we keep going. So so we're gonna consider we need to prove that every convergent sequence is a Cauchy sequence. So let's consider a sequence that is convergent to a point. So let's say converge to 8. So that's what I said. Let E sub n be a convergent sequence to 8. Okay. So that's the first part. So what is the hypothesis? The hypothesis is that you have a convergent sequence. You need to put a number, 8. Okay. Next part, what does it mean? By definition, if you choose epsilon, there exists an epsilon. Oh, sorry. No, that one. There exists n such that n a positive integer, right? Such that a sub n minus a is less than epsilon for all n bigger or equal than n. Okay? Okay, that's so far what I have. Now I need to know, what do I want? What do we need? So by definition, it says I need some m, maybe that's not the same n that I'm considering, such that an minus am is less than epsilon for all n than n bigger or equal than n. So I need that when I get a big number, two elements of the sequence, a higher number, I mean, in the index, they are big, the difference is less than epsilon. So I mean, they're getting close to each other. So that's what I want. So I want an minus mn less than epsilon for n bigger or equal than, so let's call this one n1, and then let's call one this n3. I mean, I don't know how it's gonna work. I want that. So any ideas? Any ideas for this? So there is usually a trick that and I will say triangle inequality. Okay, we proved that one last time. Remember, triangle inequality. So how could we use triangle inequality to prove this? Okay, and the other suggestion is you need to add something, to add a 0 to the sequence, and then apply triangle inequality. Go ahead. So 2 minutes. 2 minutes for that. Okay. Okay, any ideas? So we're gonna do the following. So I need an minus am. So let's see. So what I could do, I will do the following. So I need this, right? So let's consider the difference, an minus am, okay? But I cannot work with that by itself. I can work with an minus a and probably am minus a, okay? So I'm gonna do the following. I'm gonna subtract a, and I'm gonna add a, and then I got this one, okay? So minus a plus a is 0, so I haven't done really anything, right? So by triangle inequality, this is less or equal than an minus a plus a minus a m, okay? But look at that. If I choose n and m bigger or equal than n1, this will be less than epsilon, right? So I'm gonna fix this a little bit. So let's consider n and n bigger or equal than n1, right? So now I can rewrite these guys like an minus a plus an minus a, because this is the absolute value. I can put it like that, right? It's the same actual a minus an that an minus a in absolute value. They are the same because it's the distance. It's the same, the distance from here to here than here to here. So the same thing. And look at, I'm gonna make it nice. So this is less than epsilon plus epsilon, right? Because since n is bigger than n1, each of them is less than epsilon. But that will give me 2 epsilon, right? And I need an minus an less than epsilon, no that 2 epsilon. Later, there are some propositions that you could use to say, oh, it doesn't matter. But you know, since you have the power, so you can choose here epsilon halves. So you're choosing epsilon, and then you use your definition of convergence of a sequence with epsilon halves. So this, instead of epsilon, you'll have epsilon halves, and then you'll have here epsilon halves, and then that's epsilon. So as I wanted. So conclusion, therefore, an minus an is the epsilon for every n and n bigger or equal than n1. Okay, so that's my proof. Okay, so let me check the book to see I missed something or the book did something different. So we can compare. Oh, and I'm sharing. Yeah, I'm sharing. Okay. So let's see how the book did. Yeah, same proof. So no, the only thing is that for this, so A to N is a Cauchy sequence. As we want. Okay. So I would like you to do that when you're studying, okay? So when I said, please read this proof, or please try to prove it yourself and read the proof in the book. I would like you to do that. So try to prove it yourself. You got it stuck, go to the book. Maybe you can keep going by yourself. You got it stuck, go to read to the book, and so on. That's kind of the basis. That's how you read mathematics, okay? You don't read mathematics like just reading like a Harry Potter, no. You have to read and work and try to prove things by yourself, especially this class. Okay, so I have, I'm gonna write some theorems. Necessarily, I'm gonna prove them. We have a theorem. Every Cauchy sequence is bounded. That's exercise 14 from the book. Okay. So there is a concept of accumulation point. Let's probably we can define it. Definition. This is going to be important to the description of the real numbers. What is the difference between real numbers and rational numbers? Let S be a set of real numbers. A real number is, a real number A is an accumulation point of S if and only if every neighborhood of A contains infinitely many points of S. Okay? So, yeah. So, and this is theorem. It's kind of, that thing doesn't make too much sense, but look at the theorem. Every real number is an accumulation point of the set of the rational numbers. So that's why we have that weird definition. Every real number is an accumulation point of the set of the rational numbers. And every real number is an accumulation point of the set of the irrational numbers. Okay, so a real number A is an accumulation point of S if and only if every neighborhood of A contains infinitely many points of S. So if you get the rational numbers here, right? Let's say they're in a line. And you make a neighborhood. Let's say this is a real number. Like say X is a real number. So every neighborhood of this real number has infinitely many points of rational numbers or irrational numbers. That's kind of what it's saying. And basically, it's just to give you an idea that the real numbers are much better said than the irrational or the rational. They're kind of incomplete. So the real numbers are complete in the sense that every Cauchy sequence converges to a real number. That's the whole story. Okay? And let me finish this video. With two statements. The Bolzano Weierstrass Theorem. So this is a theorem, okay? This is really a big theorem. So Bolzano Weierstrass Theorem. By the way, Weierstrass is one of my favorite mathematicians. usually I said is my favorite mathematician. Then sometimes I like Fourier better, but Weierstrass makes very cool stuff. Every bounded infinite set of real numbers has at least one accumulation point. Okay, for me, the interpretation for me of this, because the way it's set it up is like not very clear, but for me, an accumulation point is more like if you have a big set, like they're saying you have a set there of an infinite set of real numbers. You have a set of numbers, right? From that, you can get a subsequence, and that's going to converge to that accumulation point. Okay, that's another way to present this. But probably the book is going to say this later in the exercises. But so an accumulation point is more, for me, I think it's better like there is a subsequence of that set that is converging to that point. Okay, so that's an accumulation point. There is an infinite set of numbers going there. That's what the real number is, an accumulation point of rational numbers, because there is going to be a sequence of rational numbers going to the real number, or there could be a sequence of irrational numbers going to that number. Okay, that's another way to present this theory. But books choose different, but at the end they put together the two of them with the exercises. And this is, so I'm gonna finish this video and I'm gonna leave you to prove this theorem. Every Cauchy sequence is convergent. Okay, so every Cauchy sequence is convergent. So try to prove that, and I'm gonna start my next video with that. And then we're gonna do some operations with sequences, and this looks more like calculus. So we'll see. I want to move forward, but let's see how much can I skip. Okay, so thanks for watching this video. So I'm gonna upload it.